Okay, in this video I'm showing the solution to problem 5.9 from Stallings. We have two antennas. They're both dipoles. They both have a directive gain of 3 dB. And they're separated by 10 kilometers and using a frequency of 100 megahertz. We have a transmitted power of 1 watt and we want to know what is the received power. So what I did first was I just plugged into our loss equation, which is rigged up so that the frequency is given in megahertz and the distance is given in kilometers. And when I rig it up with those units for the frequency and the distance, I get a 32.44 dB constant term out front here. I plug into that and I get 92.44 dB of loss due to the error, the distance of 10 kilometers. Notice I accidentally wrote 10 megahertz initially rather than 100, and I corrected it here. So I get 92.44 dB. And here I started calculating the received power, starting with the transmitted power of 1 watt or 30 dBm. And if I take the 30 dBm and subtract the 92.44, I get negative 62.44 dBm of received power. But in this calculation, I have not included antenna gains, okay? And so if I include the two antenna gains of 3 dB, I expect to get 6 dB more power received than the minus 62.44, and that would be minus 57.44. And I repeat the calculation down here with the antenna gains, and I get I use this equation. I've added the gains to the equation, and indeed I get minus 56.4, which is 6 dB. Is that correct? 6 dB off of the 62.4. Yep. And I had to correct the whole thing after starting off with the wrong frequency. In any case, I get negative 56.4 dBm of received power. And that is 2.29 times 10 to the minus 6 milliwatts, or 2.29 picowatts. Okay, that was a pretty straightforward problem. Let's see, it looks like it's continued here. Oh, here's an alternate solution. Yeah, this is an alternate solution that uses the non-decibel version of the loss equation, which is using the inverse square law, essentially, and I plug into that. And 3 dB gain is a factor of 2 for each of the two antennas. And if I do the calculation correctly and get it, I get 2.28 times 10 to the minus 9th watts, or 2.28 picowatts. Okay? And so, apparently I've made a note here that Stallings used a frequency of 300 megahertz in his solution rather than 100 megahertz. So in any case, these are the 2.28 picowatts and minus 56.4 dBm is the answer. Hope that helps.